Hey all, so this is section 0.3 for Math 116. This is about integral exponents. So we have this kind of list of properties of exponents. The major ones are 1, 2, 5, and probably 4. So for property 1, when we're multiplying, we add exponents, which gets confused a lot with property 2, where when we're raising to a power, we multiply exponents. So multiply means add the exponents, and then raise to a power means multiply the exponents. And then property 5 down here is the division one, and for division we subtract exponents. These two just pretty much say anything inside parentheses gets the exponent. Property 4 is if we have a negative exponent, we can move it to the denominator, that makes it positive. And if it's in the denominator, we can move it to the numerator, and that makes it positive. And something isn't considered reduced if it still has a negative exponent, so we use this one to simplify. And then last one down here is if we have a fraction to a negative exponent, it's the same thing as having the flip over of the fractions, the reciprocal, to the positive exponent. So let me show how that will work in context. So these first two are to kind of show the difference between these, and this is something folks can confuse a lot. So if I have negative 5 to the 4 and it's in parentheses, that literally means I have 4, oops, see I said 4, so I wrote 4. I did it again. That this has 4 negative signs. And so it's negative, 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 which will make positive, and then 5 times 5 times 5 times 5, which makes positive 625. This one, on the other hand, this really means we have negative 1 times 5 to the 4th. So that's like negative 1 times 625, or negative 625. So when there's parentheses, you're actually multiplying the negative. If it's just out in front, the negative's happening after the exponent. This next one is a negative exponent rather than a negative base. And so this would be 1 over 5 squared using property 4. And then squaring the 5 gets us 25. This one was using property 6 and just says the 2 and the 3 both get cubed. So 2 cubed would make 8 and 3 cubed would make 27. This was using property 7. So because I have a negative exponent of fraction, I'll flip over the fraction and then change the sign on the exponent. So then 3 squared makes 27 and 2 squared makes 8. This one, so we're multiplying, so that was property 1. And this plain 5 here actually has like a little invisible 1. So it's 5 to the 3rd, 5 to the 2nd, 5 to the 1st. So we're going 5 to the 3 plus 2 plus 1, because we multiply, we add, and that would be 5 to the 6th. And I think these ones want you to leave it with the exponent. You'll see the directions on the homework. This one's a division, so it means we subtract 5 to the 7 minus 2. So that's 5 to the 5. And then this one's a raised 2, so that means we multiply. So 3 to the negative 2 times negative 3 makes 6. And these are the ones that have you guys try. So negative 3 to the 5th, that would be 5 negative signs, so our answer would be a negative value. And then 3 to the 5th is 243. Negative 3 to the 4th, so this one, the negative isn't being worked on by the 4. So it'd be like negative 1 times 3 to the 4th. And 3 to the 4th is 81, so that makes it negative 81. And this one came out a negative this time because it was an odd power. On the example I just did, it was an even power, so it came out positive. 3 to the negative 3, again, that's not a negative base, so it's not a negative number. It means it's a fraction, so that's 1 over 27. 3 to the negative 4, that's the one that goes with this, so that's really 4 negative 3's, so that would be positive 81, because we'd have an even number of negative signs. This would be 2 to the 5th plus the invisible 1 right there, plus 3, so that makes 2 to the 9th. And then this last one, it would go 8 minus 6, so that would be 2 squared. And like I said, I think the directions on these ones specify to leave it with a positive exponent. Okay, these next ones use variables and exponents. And then we ran into our last thing from this sheet, which is anything to the 0 is 1 as long as it's not 0 to the 0. So looking at this next one, x to the negative 5th, that's going to be in the denominator. because of the negative exponent. Y squared would stay put where it is because of the positive exponent. Z to the 0, that's just 1, so we can just leave that off. So this would be our simplified form. For this one, there's two ways we can look at it. X to the negative 6 plus 2 is probably the easiest way. And then that's going to be x to the, adding those, I get negative 4. So that will be 1 over x to the 4th. The other way that you can think of it is that 6 comes downstairs, and if I thought of canceling out 2 top and bottom, I would have 4 x's left in the denominator. But either way works great. For this one, I'll do the subtraction. So x to the 5th, and it'd be minus, and then careful with the signs, a negative 9. So that'd be x to the 14th. And then this one, it'd be negative 5 times 2, because it's raised 2, so it's multiply. Negative 10, again, we can't leave that negative, so x to the 10th. And these two are just a little bit bigger, but using those same properties. So when we have coefficients, we just multiply those. So negative 2 times 4 would make a negative 8. And then this is x cubed, and then plus a negative 4, and y to the negative 1 plus negative 2. So if I clean that up, then I have x to the negative 1 and y to the negative 3. So this negative here is just meaning it's a negative number, so that's going to stay negative 8. But the negatives on the exponents mean they need to be in the denominator. So over x and y cubed. This next one's a division, so I think I'm going to write it to look like that. And so this will be negative 12 over 3, so I'll be a negative 4. And then x to the negative 4, and then it's minus 2. Y and z to the 3rd minus 5. So negative 4, x negative 6, y, and it looks like z is to the negative 2nd. So again, this is just a negative 4, it's not a 4 to the negative 1. So the 4 would stay up top, and the y would stay up top, so they have positive exponents. And then those two with the negative exponents would drop down to the denominator. Okay, and these next 5 are the matched problems I would have you guys try in class. So negative 4 and negative 9, so we'll add those together and get negative 13. So that'll be 1 over x to the 13th. The next one with the double negative, so let's go x to the negative 5th minus a negative 8. And then that would be x to the negative 5 plus 8 would make x cubed. You could also think of them both flipping and going x8 up top, x5 down below, canceling 5 of them, and getting x cubed. Number 12, negative 7 and 3, so this would be x to the negative 21, we're multiplying, and then 1 over x to the 21st. So here we'd have negative 5 times 2 makes negative 10, x to the 4th, and then x to the negative 5th. That's going to make 4 plus negative 5 makes negative 1, and then y to the negative 1, so negative 1 plus negative 1 makes negative 2. And then to finish simplifying, we write with positives, exponents, so x and y squared. Okay, I changed my mind and I'm going to rewrite it. So 6x negative 7, y to the 4th z, and then 2x9 z6. So right here we'd have a negative 3. This would be negative 7 minus 9, so that's going to be x to the negative 16. 4, that's the only y. And then 1 minus 6 would be z negative 5. And then rewriting that, negative 3 stays upstairs because it's not negative, not to the negative first. Y to the 4th is upstairs, and the 2 negative exponents drop down. These ones seem like kind of a funny way to write something, but if you have to take 148, you'll end up doing this a lot. So write the expression in the form c x to the n, where c is constant and n is an integer. So we want to make this look like c times x to the some power, basically. So for this first one, c would be the 8 and the 3. So I can just think of that as 8 thirds out front. And then x, to bring this up out of the denominator, I would write it to the negative 11th. And I realize at this time that why would you ever want to do that isn't maybe clear, but once you hit the derivatives in calculus, you'll like that form a whole bunch better. 16, kind of the same idea, so this would be squaring this, that negative, that make two negatives, so it'll be a positive x squared, and then 4 squared would be 16. So just to make it look like that, we'll rewrite it as 1/16 would be the coefficient, and then x squared. Number 17 is just really kind of getting you used to reading these sorts of things. So if $P is invested for n years at a rate I as a decimal compounded annually, the future value, which means how much money you're going to have in the future, that accrues is given by the formula S. So S is the future value, and then all the stuff we just talked about. And then the interest earned is the future value minus present value, so how much you have later minus how much you started with. Find S and I given P, N, and I. Okay, so first let's write down what we know. So we are looking for S and we're looking for I. And we know $P is the amount invested, so we're investing $1,500. And T, did they use T? Nope, they used N, is the number of years. And then I was the interest rate as a decimal. And so if we want to find the future value, which we do, we can do S equals P 1 plus I to the N. So that would be S equals 1,500, and then 1 plus 0.12 raised to the 5th power. And then we can, write that a little bit more simply, which I'll do in future ones as 1.12 to the 5th. Pretend like that looks like a 1. And then from there you just throw it in the calculator. So 1,500 and then times 1.12 raised to the 5th. And then we get this, and then we're supposed to round to the nearest cent. So that would be 2643.51. And then we're supposed to find the interest also. So the interest is the future value, S, minus the present value, how much we're starting with. So I would just equal this value we found, minus the original 1,500. And if you do that, you should get I equals 1,143.51. Okay, and this last one, national healthcare expenditures, H in billions of dollars, so that's another one of those ones where it's in billions, can be modeled by the formula that, where T is the number of years past 1990. So this is going to be our T equals 0, and we'll count from there. So first off, what T value corresponds to 2012? So 2012 is 22 years after 1990. So for that one, T would be 22. And approximate the national healthcare expenditure in 2012, round to one decimal place. So for that, we would just be going H equals 738.1, 1.065, and then our T is our exponent, so that's 22. We just toss that in a calculator, and to one decimal, I got H to be 2949.9.